This is the second video in a series devoted to proofwriting and in fact a course that I'm teaching in proofwriting at my college. And so in the previous video we looked at the very basics of sets, and here we're going to look more at the basics of sets. And all of this is really just to give us some tools to work with so we can start writing down some proofs. So now let's start by looking at the intersection and the union of two sets. So let's say we're given sets A and B. We can define their union, which we read this as A union B, to be everything X such that X is in A or X is in B. So union is like the conjunction or. And there's a typical way to draw this or visualize this via something called a Venn diagram. So you think about this circle here being everything in A, this circle here being everything in B. So notice we're shading everything in A or everything in B, the total of A and B. Then the intersection, which we read as A intersect B, that's going to be all X such that X is in A and X is in B. So intersection is like the conjunction and. So here we've got our same picture, but now we just have this sliver between A and B. So notice everything within this sliver is in A and it's also in B. Whereas up here, we definitely have things in A and B, but we've got elements over here that are only in A, and elements over here that are only in B. Then finally, we'll have the difference between two sets. And so A minus B is equal to all X that are in A, but they're not in B. And I use this slanty minus sign, but some authors use this just straight minus sign. So if you want to draw that, well, notice we've got this drawing right here. We have A and B, and over here, this shading in yellow is everything in A that's not in B. So that excludes the intersection because those elements are in A and B, but you don't want them to be in B. So let's look at some simple examples first before we look at something a little bit trickier involving maybe sets of real numbers. So let's say we've got these three sets. A, which has A, B, C in it, so little a, little B, little c, little d. Let's say capital B has C, D, E in it, and capital C has E, F, G in it. So let's calculate A intersect B. So for that, we're going to look for everything that is in both sets. So A and B are only in capital A, so we don't use those. C and D are in both though. So A intersect B is just the doubleton C and D. Now notice we do not include E because that's only in the set B. Now let's look at B union C. So that'll be everything in B and everything in C, or everything in C. So it's a little bit tricky because naturally you kind of want to put the word and there, but it's not really as precise as we want to be. So that will include C, D, and E. So we've got C, D, and E. Those are in B. And then we go over here and look at C. Notice C also contains E. Well, we've already got that written down, so we don't need to write it down twice. And then we'll have F and G. Now there is a way of writing down E twice, something called the disjoint union, but we won't cover that just now. Now let's look at this. We've got A union B intersect C. So later we'll be able to rewrite this, maybe by distributing the union over the intersection, but we're not going to do that just yet. So let's do this maybe from inside out. So we'll do these parentheses first. So that'll be A union, and then B intersect C is simply the singleton E. That's because that's what's in common of B and C. But now let's go up and look at A, and A does not contain E. Okay, but it contains A, B, C, and D, and since we're doing a union, that's okay. So here our set is A, B, C, D, and E. We get the first four from the set A, and then the last one from our intersection. Now let's look at this set difference, A minus B. So there we're looking for everything in A that is not in B, but that clearly is just little a and little b. Now we've got another one of these. We have the Cartesian product of A and B minus C. So that's going to be the Cartesian product of A with, well, let's see, B minus C is the doubleton CD. So we've got a set containing 4 elements. Cartesian product with a set containing 2 elements. So that should give us a set containing 8 elements. And those 8 elements are ordered pairs. The first entry comes from A, and the second entry comes from this doubleton CD. So we'll have something like this. So maybe AC, BC, DC, and CC. So that comes from choosing A, B, C, and D and pairing it with C. And then we could choose each of these and pair them with D as well. That'll give us our 4 other elements. So we'll have AD, like I said, BD, like I said, CD, like I said, and DD, like I said. And for some weird reason, I put these like, maybe they're not really out of order because the order doesn't matter, but it's not the natural way that we would have written that down. I think my brain just did something weird there. So now let's look at B minus A. Well, we already calculated A minus B and saw that it was A comma B, and in fact our subtraction is not going to be commutative here. Well, normal subtraction is also not commutative. So here we're looking for everything in B that is not in A. Well, that's just going to be the singleton E. So here we've got the singleton E. So here are 4 examples of these set operations on sets of real numbers. And we'll approach these by making a bit of a picture of what's going on. I think that'll be a nice way to visualize what's happening. So let's get our real number line for this first one, and let's shade these as I'm color coding right here. So let's see, we'll need 4 numbers to make sure we know what's going on here. We'll need 0 to 1. Actually, now that I look at this, this should have been 10, although that will also work. So we've got 0, 7, 10, and 12 are the important points for this problem. Now let's shade everything between 0 and 10. I'll shade it below just so it doesn't get in the way. So we're gonna include 0 and 10, so we need closed circles. Then everything between 7 and 12. So let's color code that orange. And now we're looking for the intersection of those. So since we're looking for the intersection of those, we need numbers that are in both of those sets. Well, I think that's pretty clearly going to be everything between 7 and 10. And we're allowed to include both 7 and 10. So here we can make this nice simplification to the interval 7, 10. Now let's look at this next one. We've got the closed interval -1, 6 minus the closed interval 2 to infinity. It's closed because this infinite thing doesn't make it open on that side. It actually makes it open and closed on that side. So let's do the same thing here. Maybe we'll keep our same color coding. So we've got orange there, we have yellow here. So the important points to write here will be -1, 2, 6. So let's write -1 here, 2 here, and 6 here. And I don't really need to worry about scales. This is just to kind of get an idea of what's going on. Okay, so -1 to 6 will be this interval as I'm shading in yellow. And then let's see, 2 to infinity will be this thing that I'm shading in orange. And I'll put an arrow to say that we're going forever. And now notice we're doing the set minus here, the set difference. So we want everything in this yellow set that is not in this orange set. So that's going to include things like -1 all the way up to the number 2. But in fact, it will not include the number 2 because 2 is included in this other set. So in the end, we get that red shaded bit, but we can rewrite this as the half open interval from -1 to 2. Okay, so now let's look at this one. So here we'll have important points of -3, 0, 3, and 5. So let's see, -3, 0, 3, and 5. Again, let's color code just to keep everything consistent. And we'll have -3, 3 looks like this, whereas 0 to 5 looks like this. And now we're trying to find the union there, but notice the union is going to include everything between -3 and 5, not including the endpoints. Oh, I got my colors off a little bit, but that's okay. In fact, maybe these are better color choices because yellow and red makes orange. Okay, so putting this together, we see that we have the open interval -3 to 5. Okay, so now let's look at this next one. We have the entire real number line minus this interval from -1 to 1. So let's get -1 and 1 on this, so -1 and 1. And then we'll see that the real line will just be everything here in yellow, whereas this -1 to 1 will be this orange that I'm putting underneath. So we want to take the orange bit away from the yellow bit. So we cannot include -1, we cannot include 1, but we can include everything branching off from that. And then probably the easiest way to write this is as a disjoint union of two open intervals. So we'll have -∞ to -1 for this left-hand bit, union 1 to infinity. Okay, so let's keep going. Now that we know about the set difference, the next logical thing to look at is something called the complement of a set. But in order to talk about the complement of a set, we need to know what context we're working in or what universe we're working in. And so I have this little remark to kind of describe what I mean by this. So depending on the context of the problem you're working in, we may want to define something called a universal set that contains every set that we might be interested in as a subset. So here are some standard examples of universal sets, although this list could be much larger. So you could have all of the numbers 0, 1, 2 up to n. That would be like a standard finite version of a universal set. You could also maybe have the set of all letters in the English alphabet, or I guess it would be the Latin alphabet. You could have the set of natural numbers, integers, rational numbers, real numbers, or complex numbers as well. And as you might imagine, you can also have like R2 or maybe Z cross R or whatever. You can really work with any universal set you want. These are just some standard examples. Okay, now that we've got that taken care of, let's suppose that we have a universal set U and A is a subset of U. So let's say for a certain class of problems we're working on, we don't need to consider anything larger than a certain universal set. Then the complement of A, sometimes you would actually say the complement of A in U, but we'll just say the complement in A, the U is understood. We'll write that as A bar, so a bar over it, and that is U minus A. But there's some different notation depending on which textbook you're looking at. You could also have A complement, so we've got that superscript C, or sometimes A prime. I bet there's more notations as well, but as I've seen, these are the most common. Okay, so let's look at some examples. So let's say we've got a universal set, which is all natural numbers, or I guess I should say all integers between 0 and 10. And then we've got A is all of the even integers in that set, and B is all of the powers of 2 in that set. So 1 is a power of 2 because it's 2 to the 0. Now let's calculate a few things. So let's calculate A complement first. So that's pretty straightforward. We have 1, 3, 5, 7, and 9. Those are all the odd numbers. That's pretty obvious. All of the complement of all of the even numbers should be all of the odd numbers. And then B complement will be, let's see, we'll start at 0, and then we get 3, 5, 6, 7, 9, and 10. So those are all of the non-powers of 2. So now let's do some combinations of this complement action with union and intersection. So let's look at the intersection of A complement and B complement. Okay, so we need to find numbers that are in both of these sets. So 1 is only in this first set, 0 is only in the second set, but 3, 5, 7, and 9 are in both of them. So 3, 5, 7, and 9. Now let's do something a little different. Let's take A union B and then complement that. So we're taking the union before taking the complement. So let's take this union first. So we'll have 0, 1, 2, 4, 6, 8, and 10. So that's a combination of all of the even numbers and all of the powers of 2. Now let's complement that and see what we get. Notice the first thing that we're missing is 3. I guess I should say we're looking for things in our universal set that are not here. So we're missing 3, we're missing 5, 7, and 9. Now you've probably noticed that these two sets are equal to each other. And in fact, this is true for any set. And that's something that we'll prove like in the future. Okay, now let's look at another example. Let's maybe look at the example where our universal set is all real numbers. And let's do something like this. Let's find the complement of the interval between 1 and 12, including 1 and including 12. So that's pretty similar to a problem we did on the previous board. So we want everything outside of this interval. So that's going to be everything from minus infinity to 1. We're not allowed to include 1. Then we can pick back up at 12 without including it and go forever. So that would be the complement in this case. So what about this? What about the complement of the integers? Well, the complement of the integers can be written as an infinite union. So notice that the union So notice that we'll need the open interval between 0 and 1. We have to take out 0 and take out 1. But then we'll also need the open interval between 1, 2, 2, 3, and so on and so forth. And we also have to go backwards. So this would be the open interval between -1 and 0, ... So we've got this infinite union of things like that. And actually the necessity of writing this complement of integers as an infinite union brings up the next thing that we'll look at, which is indexed sets. Now we're ready to look at the notion of an index set. So how this works is we have any set I, and it's really important that we can actually have any set I as our indexing set. So this capital I, like I said, will be called our indexing set. And then for any element little I in capital I, there is some set that we can attach to that element, and we'll call that set A sub I. Okay, so the logical thing to do would be to talk about intersections and unions over these indexing sets. And the notation for that goes like this. So this would be the intersection over all I of the A sub I. And this is all x such that x is an A sub I for all I in I. So you can think of a for all conditional as being like a bunch of ands stringed together. And so this could in fact be like some sort of continuous and state. So x is in A1 and A2 and A3 and A4, so on and so forth. But the important thing here is that I doesn't have to be a discrete set. It can be a continuous set, like for example, the real number. And then the union over all I in I of AI is all x such that x is an AI for some I in I. So it only has to be in one of them. It could be in 1, 2, or 3. It could be in all of them, but it only has to be in one of them in order to be in the union. So let's look at some examples. So let's start with I being natural numbers. That's kind of a classic indexing set. And then A sub I is all of the numbers between I and I squared. So notice that A sub 1 is going to be everything between 1 and 1 squared. Well, that's just the number 1. Notice that A2 will be everything between 2 and 2 squared. Well, that'll be 2, 3, and 4. A sub 3 will be everything between 3 and 3 squared, so that'll be everything between 3 and 9. Well, now we can immediately see that the intersection here will be empty. And we'll write it like this. So the intersection from I equals 1 to infinity of A sub I is the empty set. So when you've got an indexing set of the natural numbers, it's kind of classic to write the intersection like this, I equals 1 to infinity, instead of like over all I in the natural numbers, although either one would be correct. And we see that's the empty set because there's no single number that's in all of those sets. In fact, the number 1 is only in A1, it's not in any of the others. And then what about the union? Well, I think it's pretty clear here that the union is just going to be all natural numbers. And that's because the number I is in A sub I. So let's say we want 45. Well, 45 is going to be in A sub 45. It's going to be in something else, but it will be in a sub 45. So that allows us to get all of our natural numbers. Now let's look at our second example. So we've got I as the integers, and then a sub I is the open interval from negative I to I. Actually, I'm going to change this a little bit. Let's change this to the open interval between I minus 1 and I. I think that's a little bit more interesting, and it'll go back to a previous example. So now maybe let's look at a couple of examples. So a sub 1 will be the open interval between 0 and 1. A sub negative 3 will be the open interval from negative 4 to negative 3. And again here, if you take the intersection, so the intersection from I equals minus infinity to infinity of a sub I, that's still the empty set. And that's because these in fact don't overlap at all. But what about the union? So the union over all I and z, and I'd like to point out that if you're working with an indexing set of the integers, it's kind of similarly typical to write our indexed union as intersection in one of these two ways, but both of them are fairly typical. Okay, so the union here will in fact be r minus the integers. And I think that's pretty clear just by the structure of how this is going. Well, you could have a finite indexing set as well. What if our indexing set is the set 1, 2, 3? Then we've got three sets A1, A2, and A3. So let's notice in this case, the union from I equals 1 to 3 of AI, well, that'll just be the union of those three sets. I think that's going to give us the numbers 1, 2, 3, 4, 5, 6, 7, stop. So all of those numbers right there. And then we've got one last example where we've got a continuous indexing set, which is the closed interval 0 to 1. I'm actually going to do that more properly on a clean board. So now we're going to look at our example where we have a continuous indexing set. Here the indexing set is all real numbers between 0 and 1. And typically if you have a concrete continuous indexing set, you'll use alpha as your indexer. Now, if you're working abstractly, you'll generally use the I, although it's not right or wrong to do either. Okay, so for some real number between 0 and 1, we'll define a sub alpha to be the rectangle alpha comma 2 cross product with 0 comma alpha. And so like I said, this is going to be all real numbers between 0 and 1. Those are our possible values of alpha. Okay, so let's write down a couple of these sets and then we'll make some pictures. So probably most interestingly is to look at A0 and A1 because those are the endpoints. So notice that A0 will be 0, 2 cross 0, 0. But 0, 0, the closed interval, is just going to be the singleton 0. So we have 0, 2 cross the singleton 0. Now let's maybe look at A1. So that's going to be 1, 2 cross 0, 1. So there we've got a nice kind of biggish rectangle. Then let's look at something in the middle. We may look at some more things in the middle, but let's look at A1 half. So that's going to be the closed interval half 2 cross the closed interval 0 half. Okay, so now that we've got those written down, let's look at a bit of a picture. So along the x-axis, we need everything between 0 and 2. So let's maybe put 1 here and 2 here. Then along the y-axis, we'll just need things between 0 and 1. I won't keep my scale constrained here, but I think that's okay. Okay, so now let's color code this a little bit. So let's say that A0 will be drawn in yellow. So all of the x coordinates go between 0 and 2, but all of the y coordinates are just simply the number 0. So that means we've got this line segment here that's along the x-axis or along the horizontal axis. So that's our A0 set right there. It's that line segment. Now let's look at A half. So that's going to be a rectangle. Notice the x values are between half and 2 and the y values are between 0 and half. So let's go to y equals half right here. X equals half right here, and we're allowed to have this rectangle. So that right there would be our A1/2. Next up, let's draw A1. So A1, all of the x coordinates can be between 1 and 2, so just between 1 and 2, and then all of the y coordinates are between 0 and 1. So that'll be something like this. So there's a nice picture of A1. And then maybe to fill in just a little bit, let's calculate A3/4, and then maybe as a bit of an exercise, you could do A1/4 or some more of them if you'd like to. So A3/4, all of the x coordinates are between 3/4 and 2, whereas all of the y coordinates are between 0 and 3/4. Let's maybe make this in this nice magenta color. So let's see, between 3/4 and 2, those are our x values. So 3/4 is about there, and 0 and 3/4, so those are all of our y values. So we've got a rectangle that looks something like this. Okay, nice. So I'd say it'd probably be a nice exercise to play around with this some more. I think this makes some nice pictures. Okay, so now let's look at some bigger ideas before we leave you with some warm-up exercises. So now we're gonna look at a few bigger ideas. The first is the well-ordering principle. So that says that every non-empty set of positive integers has a least element. And this should be quite clear. So notice if we try to make a non-empty set of positive integers like 3, 4, 7, 1001, it most definitely naturally has a least element. In this case, it's 3. This is not true over the real numbers or even over the rational numbers though, if you take positive rational numbers. Let's consider the set of positive rational numbers: 1, 1/2, 1/3, 1/4, 1/5, so on and so forth. So all of the reciprocals of natural numbers. This does not have a least element. You can always find one of these fractions that's smaller than anything else that you want. So something that follows from the well-ordering principle is called the division algorithm. And that says for all integers a and b, there are unique integers q and r such that a equals b times q plus r, and r is between 0 and b. It's allowed to be 0 but not allowed to be b. So this is your typical division with remainder that you learn in grade school. So for instance, 14 is equal to 4 times 3 plus 2. So if you divide 14 by 4, you get a quotient of 3 and a remainder of. So that's what's going on there. And so I'll maybe like start the sketch of the proof of that up at the top here, but we won't really finish it off. We'll do the proof of that a little bit more carefully later. So let's say we fix a and b, and now we're going to consider the following set. And that set will be made up of everything of the form a minus b times x, as x ranges through all integers, and then we'll take that set and then intersect it with all non-negative integers. So in other words, this thing right here has to be bigger than or equal to 0. Now we'll call that set S. And so maybe the step number 1 here is to show that S is non-empty. Well, clearly S is a set of natural numbers. Well, not exactly. It could include 0, and we're not taking 0 to be a natural number, but the well-ordering principle is satisfied by the positive or non-negative integers, so that's okay. So S is not the empty set. You can check that fairly easily. When we do the proof carefully, we will do that. Then next, we'll take the minimum element of S to be R and let Q be the corresponding X that makes that R. But then let's notice that we'll have R is equal to B minus, or is equal to A minus B times Q, which gives us this equation down there. Now we just have to check that R is the correct size and the uniqueness. But like I said, we'll do that more carefully later when we're into our proofwriting part. Okay, so finally I want to talk about something called Russell's paradox, which is related to this fact that the collection of all sets is not a set. So it's going to consider the following collection of objects, and that will be A, and it's made up of all sets X such that X is not an element of its set of itself. So notice that A is non-empty. We can find things inside of A for sure. Notice the empty set is an element of A. That's because the empty set is a set and it doesn't contain anything. So that means it cannot contain itself. Then a bunch of other stuff is inside A as well. In fact, all maybe typical sets are inside of A. Like Z is an element of A. So Z contains all integers, but it doesn't contain the set of all integers. But can we find something not inside A? And we can, but it's kind of a crazy object. So notice if we set the set B equal to this kind of infinite collection of empty boxes, then this B is definitely inside of itself. Notice it's right there inside of itself. But since it's an element of itself, that means that B is not an element of A. So now that really brings us to the following natural question, and that is A an element of itself? Okay, so let's see. So case number one. So case number one is yes, A is an element of itself. But notice in order to be inside of A, you're not allowed to be an element of yourself. So being an element of yourself implies that you are in fact not an element of yourself if you're this whole set A. Okay, so now let's look at case two. So case one is impossible because it brings us to this contradiction. Notice we've got these two feuding ideas. So case number two will be no. But if it's not an element of itself, then by the definition of A here, it means it is an element of itself. But again, that's another contradiction. But that means we can't determine if A is an element of itself. And like I said, this is a paradox, but this is a paradox that's connected to the collection of all sets not being a set. And so while we're doing really basic ideas of sets right now, we're not doing this like higher end set theory in this course. Okay, so I think I'm gonna leave everyone with some warm-up exercises. So here are two nice warm-up exercises based off what we've done. So let's start with two sets A and B. They're both doubletons. A contains 1 and 2 and B contains 2 and 3. Then there are these 6 things to calculate. So A cross B intersect B cross B. The power set of A intersect the power set of B. A cross B intersect B. The power set of A union B. A cross B set minus B cross B. And then finally the power set of A union the power set of B. Then next let's simplify the following intersections or unions of indexed sets. So the intersection over all real numbers alpha of the singleton alpha cross 0, 1. And then the next is the union over all natural numbers, or sometimes you would write that as the union of I going from 1 to infinity of the closed interval from I to I plus. And that's a good place to stop.